Welcome back. In this lecture, lecture number 8, we will cover the different modeling approaches. So, the different concepts covered are on different modeling approaches and different modeling considerations. So, land use transportation models could be of two different types. The first type is where the land use state of a particular location is simulated. That means we trace how land use of a particular plot or a particular area changes over time. And the second type is to determine the behavior and decision of groups of land user from which the land use is deduced. That means based on the behavior and decision of different groups which actually use the land, we determine what sort of land use they are choosing or what sort of land use they are buying or what sort of land use they are renting. So, these are the two different kinds of models, and models can be both deterministic or probabilistic. And in probabilistic models, land use for a location is determined based on its estimated probability. So, it is not a fixed type. We have to determine based on probability there is a chance of a person to choose another land use. So, there has to be some way to allocate a particular land use to a particular person. So, that will be covered in a different lecture, but it's a probability model is more robust. And then models could be sector specific or integrated models. Sector specific models focus on an individual system, that is either housing or employment and so on, whereas integrated models incorporates feedbacks from other models based on their interrelationships, and so that it can update itself over a period of time, and that also makes this integrated models more robust compared to sector specific models. So, the different modeling approaches that we will discuss in this lecture are pure statistical models, cellular automata models, optimization models, rule-based simulation models, agent-based simulation models, and microsimulation models. So, these are the different approaches to modeling of urban land use and transportation. So, pure statistical models, as you can understand from the term itself, that these are based on statistical regressional analysis, and they don't necessarily follow any theory which is theories like we discussed in the earlier lectures, for example, the location theory or the spatial allocation theory or the social theories. So, these are primarily based on certain hypotheses, certain assumptions, and they are based on the existing data that is there or past data, past land use change data that is taken into consideration. Then running a regression, we can predict what would be the future land use. So, these models, because they ignore the theoretical foundation, they may be suitable for only smaller time horizons and also for business as usual scenarios, because if you take longer time horizons, then you require the theoretical background to understand why people choose certain things or why a farm chooses a certain or what rather determines the choice behavior of a particular farm. So, you require a theoretical foundation. If that is absent, you may lead to wrong predictions, because you are only doing your prediction based on data or patterns that you are seeing for some previous periods and not finding the causality why it is happening. So, these are pure statistical models, and then there are cellular automata models, and in this cellular automata models is primarily that came out from the geography discipline. And it is based on, and it predicts, it can predict urban growth, it can predict change in form, many things, but at the same time, they also don't have any economic background to that. So, there are some critique to these models as well. So, CA models are based on cell-based ideas, which were used to simulate growth, particularly in the Detroit urban areas during the 1970s, and this was initiated by Tobler. And this theory says that every cell has a certain state or function, and it depends on the characteristics of the surrounding cells as well, and there are transition rules. That means one cell changes its state from its existing state to a new state based on certain rules, and it determines that this transition rules determine the degree and direction of interaction, and it also takes into consideration the policy restrictions and the physical suitability that is required to take up the transition process. So it considers policy restriction. For example, if there is a particular type of land use, like an area is already designated as industrial area, we cannot locate a residence in that particular area. Or physical suitability could be like it's an area which has got a lot of slope. I cannot put my house in that particular area because it's difficult to construct in a land which is prone to landslides and because of the slope and all. So physical restrictions and physical suitability is also included this kind of transition rules. So once these transition rules are laid out, and then if we simulate the model, we find that at the end of the model run, some new patterns appear, and this arises from the behavior of each individual cells, because we model the transition rules for each individual cells, and after running the model, overall pattern emerges, which is also known as emergence, and from this we can draw conclusions, general conclusions of trends or patterns of change in that particular urban area. So CA models has been used for determining urban form, urban growth, land use planning, and also urban and regional development and planning. So these are different areas CA models are used. And in geographical information systems, CA model is often used on raster data to model urban growth. And CA model, as I told you earlier, that CA models lack the theoretical underpinnings of urban economic theory primarily, and transportation is also not considered in this particular model. We only look at the change in land use. So if I look at the typical structure of a CA model, you can see it starts with data collection over here, and then we determine what are the factors or our characteristics or features that we will consider for determining urban growth, and then we identify out of these attributes which could be put into the CA model for formulating the transition rules, and then CA transition rules are formulated, and then after we validate the model by seeing the changes, what it is happening, and then if it is final outcome is fine, we go ahead and say and predict the urban growth. If it is not, we keep on validating it till it gives us results which matches with earlier. Like for example, we take the data for the last 10 years and we see that okay, if the model is predicting it rightly for the current period. If that is validated, then only we apply the model for today's land use, and then we can predict for future land uses. And finally, we can get the future urban land use patterns that could emerge in the upcoming years. So in this particular image, you can see in the first image, this is the existing land use distribution. There are protected areas, the brown ones, then there are forest areas, the green ones, and then there are agriculture areas, yellow ones, and then the urban area is this bright yellow ones. So there is also a road going along. Then we considering several factors like connectivity, then geomorphology, which includes slope, the hillshade, facilities, which includes presence of schools, shopping centers, business district, economic, land price for that particular area. We formulate, and also the rules and regulations of the land, that means some restrictions in terms of land use, then the demography of that particular area, density, growth rate, and so on, then availability of land, suitability of land for particular purposes. We define the transition rules, and once the transition rules are applied and each cell is allowed to change, then we see that from this particular existing land use distribution, where we have divided the entire area into different cells, each cell has transitioned to a new, some of them remains as they were, like forest more or less remains as same, protected areas are protected, so they remain fixed, so there is no change in them. Forest may be protected to certain extent, that means it is not encouraged, but it is still allowed. So we see some amount of change happening over here, and some amount of change also happening over here, but still a lot of forest is retained, whereas most of the agricultural land is taken up, and more particularly which are in proximity of a transportation corridor, that parts are taken up whereas ones which are further away are still retained as agriculture. So this is how a CA model predicts the change in a particular urban land use. So these are appropriate in many cases, but at the same time, for prediction of transportation, this cannot be used, and because they don't include a transportation component, and also because they don't have economic background, they are only valid when existing conditions or existing economic climate, macroeconomic climate, and all the different situations remain same. If those patterns change or those factors change, then CA models may not be a good option. Then comes another line of urban land use transportation models. These are based on optimization techniques, and where optimal land use is determined using linear integer programming. It could be also neural networks, and for an existing situation based on relationships and criteria and a decision variables. That means I will explain that in detail later, and what it means is we, instead of trying to determine what would be the urban future based on the current trends, or by predicting the current trends, or the predicting different choices by individuals or farms, we are not only predicting the final outcome, but we are trying to determine a more efficient urban future. So when I talk about efficient urban future, suppose I am trying to increase density of an urban area by doing transit oriented development. So I can say that in the decision variable, which is FSI or density, this could be, if that is increased, what would be the change, what would be the optimal land use pattern that will emerge when this FSI is increased from maybe 1.5 to 2.5. And how we can determine that? That is based on lot of relationships and criteria which links FSI with the land use pattern. So these are the different things that has to be considered, and this could be of, like, decision variable is FSI. This is a single objective. I want to increase the FSI, but there could be also multi objectives as well. So the optimization models could be both single objective optimization model or multi objective optimization model, and then this kind of models actually evolved from linear programming models of residential location to urban land use allocation problems, like how we can how we can allocate urban land use in the most suitable way. Some examples for this particular approach, we can say that model for location of green belts for air quality control, and then multi-objective optimization model for smart growth. These are some examples of this optimization techniques. But this kind of models are rare in literature, research literature. So an example, if you see this particular equation, which is talking about minimizing the transportation cost for different kinds of trips. Trip ij is the total number of trips in link j for trip purpose I, and these are the C values at the cost of different kinds of trips, and this PTJ, P and PSIJ, these are the probability of choosing fast mode, which includes car and transit, and then 1 minus PTIJ is the probability of choosing car mode for link J for trip purpose I, and so on. So basically this predicts that transportation cost of an urban area, overall transportation cost. We are trying to minimize that. So if this is our objective, then we have a decision variables which is building FSI. That means if I change FSI, the transportation cost may reduce, and we use different constraints such as minimum and maximum FAR that is allowed. That means we cannot keep on increasing FSI beyond a certain value. So there is a limit to that. And then there are a number of buildings that can be reconstructed. That means not all buildings can be reconstructed, only a certain number of buildings can be reconstructed at a higher density. Or rather, when this urban developers would be allowed to build a new or reconstruct a building, they will of course utilize the maximum FAR. So if I set the FSI as a higher value, that we will have higher density buildings, and this is linked. So FSI is linked with transportation cost using two different relationships. Some of these are between trip generation and building density. That means there could be a hypothesis like when building density increases, number of trip reduces or the length of trip reduces, or when between mode choice and building FSI density. That means when density is high, people are more prone to choose certain modes which are which will lead to lesser cost. So if this kind of relationships are there, it could be both positive or a negative relationship. If this sort of relationships could be there, we can minimize transportation cost by determining certain kind of density. So it's one density is again could be said this is one aspect of land use. So land use transportation models which are determined based on determining a better future or trying to determine a targeted future, there we can use optimization models, and these are used in limited numbers in literature in only, but they could be used for like this, certain interventions like this, like for example we are trying to do transit oriented development for a particular area, there this kind of models could be appropriate. Then comes the rule-based simulation models, and these models imitate urban processes while considering limitations arising out of government's development policies and allocates population to locations based on strict rules. So what it means is these models imitate the normal urban development process. They follow certain rules, and they will also consider the limitations that are there. For example, development is not allowed in a site which is a wetland. So it will take that limitation, and it will based on normal imitate urban process means it will try to find out how developers are developing a particular land, and which of the lands could be developed, and the ones which would be developed more, there more number of peoples could be allocated. So these are the different rules it follows. One of the popular models, one of the very famous models coming out of this sort of rules is California Urban Futures Model made by Landis in 1994, and this was applied in the San Francisco Bay Area, where here the projected population was based on past trends and is allocated following a bottom-up approach. That means we first predict the population and then we gradually allocate them at different zones. And accessibility is also incorporated, that we also check that okay, the allocation follows locations where accessibility is high, and it is also uses GIS for this particular use for this particular planning process. So geographic information system is an integrated part of this kind of modeling process. So this is the structure of the California Urban Futures Model. You can download this from this particular source, where you can see in the step 0, we first focus the basic employment growth by county. So this is the exogenous input or projection, or rather the forecast that we take into a model. Then bottom up population growth submodel is basically we project the city population for 5-year periods. Then we also project the county population for 5-year periods, and then we calculate unincorporated population growth as a residual. That means people who are not already allocated land because of this excess population growth, those people has to be, they are considered and they has to be allocated a particular land. Then we develop using GIS maps and all, we can develop the spatial database. We update the map layers with this new information of administrative boundaries and so on, and then we based on the different information that we have got, we determine what is the developable land units in a particular area. That means which are the land units which could be developed by real estate developers, and then we determine a profit potential for each of this unit. That means if I develop in those units which will return more profit, and also once we consider that, then we can say eliminate these units where there is some sort of laws preventing some development, which are like, as I told you, that it could be a wetland, so you cannot develop in that unit even though it would have been profitable. And then we start allocating the population as per the growth profit potential of each of these DLUs. So, and this is basically the process where we follow different steps to allocate the population, and this can actually result in a new land use model, or you can predict the growth of that urban area in these new developable areas, and how the new excess population would be allocated in these particular areas. Then coming to multi-agent models, here the decision, all different decisions related with land use are considered as an outcome of decisions taken by multiple agents or many agents. Now, who are these agents? These agents could be of different types. They could be the households, this could be the farms, this could be a component which determines the land price, how it changes. It could be based on a particular, a choice of a household to build or buy a car. So it could be ownership of cars. So these are the different components that are considered in this particular models. And agents are autonomous and they make choices and decisions in a shared environment while interacting with other agents. And the choice decision behavior is modeled following either rules of thumb, which is heuristics, or limited rationality or utility functions. This is similar to discrete choice that we have discussed. And limited rationality it is called because not everybody has got information about all the choices and all. So whenever a person takes a decision, it is based on rational behavior, but it sometimes we call, but it is limited to a certain extent. So we call it limited rationality, and it determines the utility of different choices and accordingly takes a decision. Decisions are also based on a cross-sectional average of relevant decision-making groups for different agents. So when we talk about utility functions or we talk about discrete choice theory, the decision could be taken by an individual or it could be taken by a group. So if the group is homogeneous, then the decision taken by the group is actually okay for all the individuals who belongs to that, or all the households that belongs to a particular group. Same also could be considered for the different farms. If the farm is homogeneous, the decision or the way it determines utility of different choices is also same. So that's why we take a cross-sectional average of relevant decision-making groups, and that we use for determining the probability of choice. So one of the models, again this is a famous model, this is Puma, which is predicting urbanization with multi-agents. This is one of the very common well-known model which is still in use. This uses the multi-agent approach. Here agents are landowners. Agents could be the authorities. Authority means the planning departments, maybe the municipal corporation who actually forms the laws and the guidelines. It could be the farms, the companies, or it could be the households. So then there are different components within this model, which is one component is the land conversion module, which includes buying and conversion of particular land, which models the buying process as well as the conversion process of a particular land. And it includes farmers, authorities, investors and developers who actually involve in this buying and conversion process. Then there is the household module, where we look into the housing and their job locations, their locations for housing and their locations for jobs. And here also we considered the transition of the household modules in terms of marriage, childbirth, aging, job change and so on. So we track this, and the daily activity patterns are also determined, based on which we can determine that amount of trips that are generated out of this particular for each household. So this is the household module. And finally the farm module, where the farm's demography and relocation process is also modeled. So these are different agents, like this different agents like the landowners, authorities. So they are connected in these different modules. They are connected to each other and they interact with each other, and they take certain decisions which follows limited rationality, resulting in a particular choice which ultimately gives the spatial which actually determines the spatial structure of a particular urban area. Next comes microsimulation. So this is the very latest approach, and microsimulation refers to simulation at the level of individual persons or farms so that the heterogeneity can be captured. So that means instead of taking homogeneous group, here we take every individual. We consider every individual is separate, so his decision making process would be different from other individuals. Same goes for farms as well. And land use and human activity changes are modeled at a realistic scale and choice level. That means this is a more realistic because every person can take a decision, and when we add up all these decisions, you get to come at more realistic outcomes. And microsimulation was first used in the social sciences discipline, And then agent-based microsimulation models of urban land use and transport, those actually were developed. Some of the famous ones are ILUT and ARPAD, Delta and UrbanSim. These are very, very famous urban land use transportation models following microsimulation. And the choice behavior of individuals is guided by discrete choice theory, as it is done in the UrbanSim model, and also following machine learning using decision trees in the Albatross model. So we are gradually now moving into the domain of machine learning to predict also the choices. So both discrete choice and machine learning approaches are used, and there we already have different model systems following these approaches, of course incorporating microsimulation, which refers to the decision of individuals or individual persons or farms for every choice that he makes in an urban area, and that results in the overall urban land use structure and form. So what are the challenges with microsimulation? As you can understand, when we are taking the decisions of individuals, definitely the final outcome is more appropriate, more realistic, and it will the models are more the results that they show are they are more near to the actual conditions. So but the problem is when not everything can be done at a very micro scale. Like for example, economic growth and demographic change, these are predicted at a macro scale. This cannot be done at a micro scale. So how do we match the regional forecast of population and jobs which are at a macro scale with micro scale choices or micro scale allocation in a particular urban area? So these are the challenges that usually people face when they use microsimulation models. And microsimulation models, as you can understand, suffers from large data requirement and computing challenges, which is understood. Then there is something called stochastic variation or Monte Carlo error, which is another major issue. What it means is whenever we run the model, whenever an individual is making a choice, ultimately even if we use discrete choice, it gives us a probability. But a certain individual has to be allocated a certain choice. So we use Monte Carlo process for that, which would be explained in detail later on. There what we find is a particular individual, we have to use random numbers to determine how an individual's choice would be the final choice based on, of course, the probability of the discrete choice model. So there, if I use different seeds for random number, seed is basically the starting of the random number, we find the results of the model different. So every time we run the model, you will see the results will differ. So it may not be differing by too much, but it still differs. So that is a question. That means so person can always ask that, okay, if the model predicts different in different times, which one should I take? Which result should I take? So in that case, a model can be run several times, and we can average the results, and that could be taken as the final result or the final outcome, either of land use processes or of transportation processes and so on. So that is one problem, and also a partial solution to that. Plus there is another problem where due to stochastic variation, when we have less number of agents and more number of choices, there also problem occurs. That means suppose there is a few companies, but they get an option to move to many plots, which could be the location of the new headquarters or new offices. So there the results vary at different runs, and that can lead to lot of variation in the results. So that stochastic variation is also another problem. And so these are the basic problems of microsimulation approaches. But still, I would say that microsimulation is the more robust one compared to all the other approaches, provided we have enough data as well as we can take care of the computing challenges. So, and the optimum level of disaggregation can also depend on each modeling task. That means for different components of the model, we can use different levels of disaggregation. That is also could be considered. So, along with the different modeling approaches, there are few modeling considerations which are also very important. This could be called as equilibrium or dynamics. Equilibrium describes a hypothetical long-term market steady-state condition in which supply, demand and prices are perfectly balanced, and all buyers and sellers have full information about prices and utility of choices. So what it means is, that means when I'm trying to determine how many number of houses would be allocated in a particular area, or how many number of farms has to be allocated in different areas, there we understand the supply of land for that farm and the demand for that farm matches equally in a certain time period. But in real life, it is not like that, because our developer realizes that there is a market potential for development for a particular kind of real estate. So he will choose to develop that, but it takes certain time for that property to be available in the market. So suppose there is a time lag of few years. So that means during that time there is a shortage of supply, so that will spike the prices. And during the other time, whenever the new a developer comes out with a property, he actually supplies more than what is required in the market, because he knows that there would be demand eventually, and that will, and he could be able to sell that particular property. And because of the condition of that particular development, he has no option but to do the full development together. So this could be the reasons why there could be cases of supply and lesser supply or oversupply, and that leads to something called boom and bust cycle in real estate. So even though housing and real estate and transport market all moves towards equilibrium, however, supply and demand is not perfectly balanced, and that is because due to limitations of the different agents, and because they are not exactly perfectly elastic, there is a time lag for this, for demand to match supply, supply to match demand, and so on. And this is one part, and the other thing is, due to inertia of growth of urban areas, sudden changes towards equilibrium is also not possible. And in the short term supply disequilibrium conditions happen. This is also supported by the systems theory and complexity theory, because there are so many small systems working in an urban area, each influencing another. Suddenly we say that the entire urban area is in equilibrium. That is not possible. So disequilibrium conditions always exist. So we have to think of this in the urban modeling process as well. Because if we think about equilibrium, it may be true for a long period, the predictions may be true for a long period, but in the short period it may be wrong. So we can see, we have already discussed this in our earlier module, that there are different agents in an urban area, different factors are there, and each of them grows at different speed, or the change is different. For example, it takes 3 years to build a house, whereas a person changes house maybe after the end of a certain amount of period, or a building is built and the life of the building is 50 years. There are different factors have got different life cycles, and accordingly we can also choose the time that we determine for this modeling process. So nowadays most of the urban land use processes are made little bit dynamic. We can call them either recursive or quasi-dynamic. What it means is, we, instead of having time periods of 5 years or 10 years as a prediction period, we predict for every 1 year, and then we again run the model, taking the output of the first year as the input for the next year, for the next model run. And this is called a quasi-dynamic process, and it's a recursive process, of course. So we can take for 1 year, it could be even stages of 5 years or so. And most of these dynamic land use models are based on accessibility based location choice models. And some of these models which are based on the spatial interaction theory are Emiplan, Tranus, and Picas. These were initially not dynamic, but nowadays they have been made into dynamic models. And then we have got bid rent location allocation models like Musa, which are right now made into dynamic models. Then the next debate comes about macro and micro. So we have dynamic and static models, and then we have macro and micro. How much micro and macro refers to the level of spatial and substantive disaggregation. That means how much, what should be the appropriate size of analysis. Like, for example, we discussed TAZs earlier in our previous module. But when we talk about disaggregation, when we are talking about microsimulation at the individual level, that means a particular farm is choosing a particular plot, or an individual is choosing a housing unit. In that case, we have to go to a much more micro scale. So if you can see in this particular image, instead of taking TSZs, a 1000 by 1000 meter grid is taken. This is the larger grid, and within this we have 150 by 150 grid. So this is a small grids, and each of these grid, if I know that okay, how many housing units are there, then once a person chooses this particular grid to move into, we can allocate him randomly in one of those housing units which is appropriate for his income group, income bracket, and so on. So or the characteristics of this particular unit influences his choice for moving into this unit. So that means the utility for this particular grid is also determined based on the amount of the number of empty housing of particular category, or the kind of characteristics this particular unit possesses. For example, does it have access to the highways? Is it mostly residential, or is it partly residential or commercial? What is the density? What is the amount of available land that is there? So all these things influences the choices of individuals. So this could be, so if it was at a TSZ level, then it's difficult to generalize these choices or form these utilities which would apply homogeneously to all plot of land or to a particular individual. So this kind of so that's why there is a need for moving from macro to micro. And earlier models, as we have discussed, are mostly zone based, but since 1990s, land use changes are modeled using high resolution grid cells. This is of course not for our country. This is mostly for US and Europe and other developed nations. And microsimulation and activity-based modeling also requires this high level of location data, and modeling using grids combine geographical information from different sources. That means we need to determine characteristics of this particular grid, which is shown here. So we take one grid. To determine characteristics of this grid, we require land records that will show us that which are the plots which are empty, which are the plots which are built, which are the size of plots, and all the different information. The economic survey, that means how many jobs are available in that particular grid. Then there is the census data on number of households living in that particular grid. It could be proportionately from the broader region in which this particular grid belongs. From there we can also determine that, or it could be determined by some other process which we will discuss later. There are other ways as well. Then we can use the existing GIS maps for environmental information, urban growth boundaries, wards, traffic zones. All these things could be also put into this particular grid. And then taking the data from all this, we integrate the data, and then we can create the characteristics of the grid. So if you can see the characteristics, there are jobs, there are different kinds of jobs belonging to different sectors. Each job has got an ID, and each grid has got an ID. And whenever a job is filled, that ID is, we can, in the modeling process, we can say that job ID is filled. So in that way, we will keep track of that. Then each grid has got ID. We measure the total number of housing units, vacant housing units, then total non-residential square feet, vacant non-residential square feet, what kind of development type, land value, and environmental overlays, urban growth boundary, ward boundary, traffic zones, and so on. So this is how we can develop the information for this particular grid. And for households, we also need to know for each household who are staying there, it will have a household ID, and then there are number of persons in that households, worker in that household, children in that household, and income of that households, and all these things needs to be known for that particular grid. So this is the level of data that we require. So as you can understand, it's very, very challenging to gather this kind of data for units like 150 by 150 meters or grids like 150 by 150 meter, and that is the challenge, or that is the macro versus micro debate. So these are the references you can follow for this particular lecture. So in conclusion, we can say land use transportation modeling is moving towards multi-agent microsimulation models. However, level of disaggregation depends on data availability and computing resources. Dynamic models of land use transportation interaction allows for incorporating the feedback cycle. This is also important. And while discrete choice theory is the popular approach to determine choice behavior, machine learning approaches are also being increasingly adopted. So this gives you a broad idea about the different modeling approaches that is undertaken in an urban area. Thank you.